June 21st, 1943. Kammhuber Line, northern Germany. The low hum in the operations bunker never stopped. Telephones rang in clipped bursts. Typewriters rattled. Cigarette smoke hung thick under bare bulbs as Oberstleutnant Friedrich Keller leaned over a plotting table marked with glowing pins and grease pencil arcs. Above him, unseen in the night sky, British bombers were crossing the North Sea. Keller adjusted his headset as a young signals officer stiffened beside him. Contact, multiple returns, range 200 kilometers, heading southeast. That alone was not unusual. What made Keller pause was the clarity. The blips on the Würzburg radar scopes were sharp, too many, and moving in formations that shifted faster than the German interception model predicted. For years, German radar scientists had believed they held a decisive edge. The Freya early warning system, the Würzburg fire control sets, the carefully layered Kammhuber line that funneled Allied bombers into kill zones of night fighters and flak. It was supposed to be a net, but tonight, the net felt porous. Keller watched as entire bomber streams appeared, vanished, then reappeared miles away from where they should have been. Radar operators called out conflicting bearings. Night fighter squadrons scrambled toward ghosts. "What's interfering with the signal?" Keller snapped. The answer came from the corner of the room, where a civilian in a rumpled lab coat stood silently. Dr. Hans Plendl, one of the Luftwaffe's leading radar specialists, stared at the scope with growing unease. "They are doing something," Plendl said quietly. "Something new. Outside, the flak batteries around Hamburg would soon fire blind. And in a quiet laboratory thousands of kilometers away, American engineers were already moving on to the next breakthrough. When the war began, Germany had led the world in applied physics, radar, rocketry, jet propulsion. Their scientists were respected, feared, and envied. Men like Heisenberg, Werner von Braun, and Ernst Heinkel had pushed technology forward at a pace few nations could match. The United States, by contrast, was viewed as a giant workshop, good at making things, slow at inventing them. German intelligence assessments from 1940 described American research as fragmented and commercially minded. Capable, yes, but lacking the centralized scientific rigor of Europe. It was an assumption that would haunt them. Across the Atlantic, in a nondescript building in Cambridge, Massachusetts, the hum was different. At the radiation laboratory of the Massachusetts Institute of Technology, oscilloscopes glowed green in darkened rooms. Engineers leaned over benches cluttered with vacuum tubes, waveguides, and coffee-stained notebooks. There were no uniforms here, no salutes, but the urgency was absolute. The British had arrived in 1940 carrying a metal cylinder wrapped in secrecy, the cavity magnetron. It was small, crude-looking, and capable of producing microwave radar far more powerful and precise than anything Germany possessed. American scientists understood its implications almost instantly. What they did next shocked everyone. Instead of guarding the discovery, they scaled it. Factories were retooled. Universities emptied their physics departments into classified programs. Companies like Raytheon and General Electric began producing components not by the dozen, but by the tens of thousands. Radar sets shrank from truck-mounted monsters into compact units that could fit inside aircraft noses, ship superstructures, even artillery shells. By 1943, American bombers were flying with radar that could see through cloud, darkness, and smoke. German analysts noticed. Intercepted reports from Luftwaffe night fighter units complained that British and American bombers were anticipating interception routes. Flak accuracy declined inexplicably. Entire raids slipped through defenses once considered airtight. Plendl and his colleagues suspected countermeasures, jamming, chaff. They did not yet understand the scale. That realization began to dawn far from Germany, in the skies over Sicily, July 10th, 1943. As Allied forces landed on the beaches, American cruisers offshore fired round after round at German and Italian positions inland. Observers watched in disbelief as shells detonated in midair above trenches and gun pits. No impact, no ground contact, airbursts. German artillery officers reported casualties from shells that seemed to sense proximity. At first, they assumed error. Faulty fuses. Luck. Then the pattern repeated. What they were witnessing was the debut of the proximity fuse, a device containing a miniature radar transmitter inside an artillery shell. When the shell neared an object, the reflected signal triggered detonation. It was physics reduced to brutality. German scientists had experimented with similar concepts but dismissed them as impractical. Too fragile. Too complex for mass production. The Americans had solved the fragility. And mass production. By late 1943, proximity fuses were being fired in their millions. Against aircraft, against infantry, against V-1 flying bombs over England. Each shell carried a tiny radio laboratory, and Germany could not replicate it. Back in Berlin, intelligence summaries grew increasingly grim. American weapons were not merely advanced. They were everywhere. Radar-equipped fighters hunted U-boats at night. Naval task forces coordinated over vast distances with precision that defied German planning models. Anti-aircraft fire grew lethally efficient. The question German scientists now asked was no longer how America had invented these technologies. It was how they were building so many of them. Because by 1944, it was becoming clear. The Americans weren't just mastering advanced weapons. They were turning science itself into an assembly line. And Germany was falling behind by the week. February 22nd, 1944. Schweinfurt, Germany. The sky howled. Major Karl-Heinz Bauer of the Luftwaffe squinted upward through drifting smoke as contrails crisscrossed the cold blue above him. The sound was different today. Deeper. Louder. Relentless. Wave after wave of American bombers rolled in from the west. B-17 flying fortresses. Hundreds of them. They flew straight, unafraid, tight formations holding course through flak bursts that bloomed uselessly behind them. Bauer's radar liaison officer shouted over the noise. "They're jamming us again! Fighter direction is blind!" Bauer already knew. This was no longer an anomaly. It had become routine. What terrified him was not the bombers. It was the coordination. Inside the Reich Air Ministry, technical briefings were growing desperate. Charts pinned to walls showed American production curves rising at angles German planners had once dismissed as fantasy. Radar sets, aircraft radios, fire control systems, new bomb sites, new fuses. Each month, the Americans introduced refinements faster than Germany could study the previous version. Dr. Wilhelm Runge, a physicist tasked with evaluating captured Allied equipment, stared at the disassembled American radar unit on his workbench. Compact, modular, rugged. "This is not a prototype," he muttered. "This is a finished product." The casing bore serial numbers in the tens of thousands. That number haunted him. German industry excelled at precision, hand-fitted tolerances, skilled labor, careful calibration. But the American device was designed differently. It was designed to be copied. Components snapped together. Tubes were standardized. Replacement parts interchangeable across entire fleets. American engineers were not building instruments. They were building systems. Across the Atlantic, at Wright Field in Ohio, Colonel Edward Montgomery watched test pilots climb from cockpits streaked with oil and frost. Engineers crowded around them, notebooks open. How did it handle at altitude? Radar lock stable at 30,000. Fuel consumption? Within tolerance. Data flowed from flight line to drafting board to factory floor in weeks, not years. This was the engine Germany had failed to grasp. The Americans had fused science, industry, and logistics into a single organism. When a laboratory breakthrough occurred, It did not stall in committees or vanish into inter-service rivalry. It moved. Fast. German intelligence intercepted fragments of the truth. Reports from Japan warned of American night fighters equipped with airborne radar that could hunt in total darkness. Submarine commanders complained of aircraft appearing without warning, guided by sensors invisible to the eye. Still, some in Berlin clung to hope. They have numbers, not genius, one senior official insisted. They copy European ideas. But by early 1944, that illusion shattered. April 1944, Peenemünde. In a windswept complex on the Baltic coast, Werner von Braun stood beside a V-2 rocket as technicians secured cables and valves. It was the most advanced weapon on Earth. A miracle of engineering. Yet even here, something gnawed at him. The reports. American bombers now carried radar precise enough to strike through cloud cover. Their bombs fell closer to targets once considered safe. Peenemünde itself had already suffered devastating attacks. Von Braun had read intelligence summaries describing American jet research. At first, he dismissed them. The United States had no tradition of advanced propulsion, he believed. No theoretical depth. Then photographs arrived. Blurry, partial, but unmistakable. American engineers were testing turbojet engines at scale, not as experimental curiosities, but as production-ready designs. Germany had flown the world's first operational jet fighter, the Me-262. Yet fuel shortages, pilot training gaps, and political interference crippled its impact. The Americans, by contrast, were preparing jets within a framework of supply lines, trained crews, and industrial redundancy. Von Braun said nothing aloud, but he understood. A weapon is only as powerful as the system behind it. That system revealed itself brutally over Normandy, June 6th, 1944. As dawn broke over the channel, German defenders listened to the roar of engines unlike anything they had heard before. Allied aircraft filled the sky, not just bombers and fighters, but reconnaissance planes, radar-guided pathfinders, airborne command posts. Every movement was synchronized. American ships offshore used radar to track shell trajectories. Proximity fuses turned air defense into a lethal umbrella. Communications flowed seamlessly between sea, air, and ground. German counterattacks dissolved under artillery that seemed to anticipate them. Field commanders sent frantic messages inland. The enemy sees everything. They were not exaggerating. Back in Berlin, scientists and officers gathered in rooms heavy with tension. Charts no longer mattered. What mattered was time, and Germany was running out. They had believed that complexity would slow America down. Instead, complexity became America's strength. Where Germany perfected individual masterpieces, America perfected replication. By late 1944, German analysts reached a conclusion they scarcely dared to record. The United States had not merely caught up technologically, it had surpassed them, and learned how to multiply that advantage endlessly. Science, once Germany's shield, had become its undoing, and still, one final revelation awaited. September 12th, 1944, Bonn, Western Germany. The American artillery fire began before dawn. General Major Ernst August Köstring stood inside a commandeered stone villa overlooking the Rhine, listening to the distant thunder roll closer. Each explosion was sharper than the last. Not random, not probing, measured. A signals officer burst through the door, breathless. Herr General, our forward units report airbursts again. Infantry losses are severe. Köstring closed his eyes. The proximity fuses. They were everywhere now. What unsettled him most was not the weapons themselves, but the certainty with which the Americans employed them. There was no hesitation, no experimentation in the field. Every shell behaved exactly as expected. Every unit trusted its equipment completely. That kind of confidence could only come from something Germany no longer possessed. Time. In a research institute outside Berlin, Dr. Kurt Diebner flipped through a thick folder marked Geheim. Inside were technical assessments compiled from intercepted reports, captured equipment, and intelligence leaks from neutral countries, radar advancements, fire control integration, jet propulsion timelines. At the back of the folder was a projection chart. American monthly output of advanced electronics had crossed a threshold that summer. It was no longer exponential. It was unstoppable. Deebner leaned back slowly. Around him, younger engineers whispered in low voices. Some stared at the floor, others at nothing at all. What we are seeing, Deebner said finally, is not superior invention. He tapped the chart. It is superior organization of knowledge. Germany still had brilliant minds, perhaps the best in the world. But brilliance, Deebner realized, no longer decided wars. That truth became impossible to ignore in the skies over Germany. October 1944. American bombers now flew with escort fighters equipped with airborne radar that allowed them to hunt even through cloud cover. Night offered no refuge. Weather offered no protection. German pilots reported being intercepted without warning. No visual contact, no chance to disengage. One veteran ace, Hauptmann Josef Priller, described it bluntly in his combat diary. They know where we are before we do. On the ground, flak batteries struggled to adapt. Radar frequencies changed faster than countermeasures could be recalibrated. Command posts were destroyed with uncanny precision. The war had become asymmetrical in a way German doctrine had never prepared for. In November, a captured German technical officer was flown to Britain for interrogation. Expecting propaganda and intimidation, he instead found himself escorted through a warehouse. Inside were rows upon rows of radar sets, proximity fuses, radios, and navigation devices stacked like ordinary cargo. The officer stopped walking. "How many of these do you produce?" he asked quietly. The British intelligence handler shrugged. "This is just one depot." The officer said nothing more. Back in Germany, the final blow came not with a bomb, but with a report. A consolidated intelligence assessment circulated among senior scientific advisors in December 1944. It summarized the situation in stark terms. American advanced weapons were no longer rare or experimental. They were standardized, interchangeable, supported by global logistics. Jet research was advancing rapidly, but more importantly, it was embedded within a training and fuel infrastructure Germany could no longer match. Radar was not a device, it was an ecosystem. Electronic warfare had become industrial warfare. One scientist scribbled a note in the margin that would later be found among the ruins of Berlin. They do not innovate faster, they deploy faster. As the Allies crossed the Rhine in March 1945, resistance collapsed in waves. German units fought bravely, sometimes brilliantly, but always outmatched by a coordination they could not disrupt. Every attempted counterattack was detected, every concentration of force targeted before it could strike. The battlefield itself had turned transparent. Somewhere in the ruins of a laboratory, Dr. Hans Plendl sat alone, listening to distant gunfire echo through shattered windows. Years earlier, he had helped build the world's most advanced radar network. Now, he understood what he had missed. Technology was no longer about invention. It was about velocity, how fast an idea could move from mind to metal. And in that race, America had not just overtaken Germany, it had redefined the finish line.